Interactive image inpainting seeks to restore complex structures and corrupted regions, leveraging user-provided sketches to guide the process. However, the free-form and inherently random nature of sketches can confuse inpainting models, resulting in severe artifacts. To address this, the proposed SketchRefiner method adopts a two-stage approach. In the first stage, a cross-correlation loss function is employed to robustly refine user-provided sketches in a coarse-to-fine manner, mitigating the impact of sketch randomness on the inpainting model. This refinement process calibrates the sketches to better align with the underlying image structure. The second stage involves learning to extract informative features from the abstracted sketches in the feature space and modulating the inpainting process. This enables the model to effectively incorporate user intentions and tolerate certain randomness in user input. The authors also propose an algorithm to simulate real sketches automatically, facilitating the creation of a test protocol with various applications. Experimental results, as shown in Figure 1, demonstrate the superiority of SketchRefiner over existing methods, such as SketchEdit, in scene editing and face manipulation tasks. While SketchEdit exhibits noticeable artifacts due to the direct use of sketches as edges in the missing area, SketchRefiner effectively reflects user intentions and tolerates certain randomness of user input. Quantitative and qualitative evaluations consistently show that SketchRefiner outperforms state-of-the-art methods, highlighting its potential in real-world applications. The publicly available code and dataset facilitate further research and development in this area. In image processing, image inpainting aims to restore missing pixels in corrupted regions while maintaining global consistency. Despite progress made by traditional and learning-based methods, challenges persist when dealing with sketch-like inputs. Edge-based image inpainting methods have shown promise, but they require pixel-wise precision and suffer from the gap between user-drawn sketches and image models, making them less practical in real-world applications. To address these limitations, we propose SketchRefiner, a two-stage system consisting of sketch refinement and image inpainting. This approach bridges the gap between sketch-like inputs and image models. The novel sketch refinement network utilizes a cross-correlation loss function to enhance its performance, extracting informative features from refined sketches and aggregating them into the inpainting network as modulation. This allows the model to produce results according to the sketch inputs. SketchRefiner makes three main contributions. Firstly, it reinvestigates the challenges in sketch-based interactive image inpainting and introduces the SketchRefiner system. Secondly, it designs a sketch refinement network with a novel loss function to robustly calibrate user-provided sketches and learn to extract informative features from sketches for modulation in the inpainting network. Lastly, it proposes a sketch simulation algorithm and establishes a sketch-based test protocol for real-world applications. Experiments on public datasets and the proposed testing benchmark demonstrate the effectiveness of SketchRefiner compared to state-of-the-art competitors. The paper also reviews related work in image inpainting and sketch-based image editing, highlighting the need for a more effective adaptation of current methods to sketch interactions in real-world circumstances. The use of sketches over edges in image inpainting offers several advantages, including improved alignment, enhanced structural coherence, and a higher level of abstraction. To refine these sketches, the SketchRefiner is employed, comprising a registration module and an enhancement module. For texture restoration, the sketch-modulated inpainting network, SIN, plays a crucial role. A significant challenge in this field is the data insufficiency problem, which can be addressed through the sketch simulation algorithm, SSA. This algorithm simulates sketches from detected edges, providing a more comprehensive approach to image inpainting. By considering the characteristics of sketches, researchers can achieve more effective results in the process of image reconstruction. The paper presents a novel algorithm, the sketch synthesis algorithm, SSA, for generating simulated sketches. This innovative process begins with the detection of the foreground and its corresponding edge using saliency and edge detection models. A Gaussian filter is then applied to create a warping map, which deforms the edge to produce the simulated sketch. Figure 3 illustrates this process, comparing the simulated sketches with existing sketch datasets and user-drawn sketches. The algorithm's pseudocode is provided, outlining the steps from foreground detection to the final simulated sketch. The sketch synthesis algorithm, SSA, is a groundbreaking approach in generating realistic sketches. It initiates by identifying the foreground and its edge through advanced models. Subsequently, a Gaussian filter is applied to create a warping map, which distorts the edge to form the simulated sketch. This process is visually represented in Figure 3, where the generated sketches are compared to existing datasets and user-drawn sketches. The algorithm's pseudocode is included, detailing each step of the process from initial detection to the final sketch. The authors introduce a novel approach to sketch-modulated image inpainting, refining sketches and utilizing them to guide the inpainting process. This refined sketch is represented as the difference map between the refined sketch and the ground truth, denoted as increment SPI and increment EPI. Two loss functions, LRM and LEM, are defined, combining pixel-wise constraint LL1 and region-wise constraint LCC. The weights of the region-wise constraint, lambda1 and lambda2, are set to 0.4 and 0.9, respectively. A partial sketch encoder, PSE, is proposed to learn to encode sketches onto the feature space and extract informative features from them. The PSE uses gated convolution in the first two layers and selects a series of coarse-to-fine features from the last four layers. These features are then aggregated to the texture restoration module, TRM, to modulate the inpainting process. Sketch feature aggregation, SFA, blocks are introduced to learn to aggregate the extracted features from the PSE. The SFA blocks project the encoded features onto an embedding space, convolute them to two modulation tensors gamma and beta, and merge them to the image features by elementwise adding and multiplying gamma and beta to the activation layers. The authors employ the TRM as the inpainting network and implement the SFA blocks in the encoder part of TRM. The overall loss function LSIN consists of pixel-wise reconstruction loss LL1, adversarial loss LADV, feature matching loss LFM, and high receptive field, HRF, perceptual loss LHRF. A sketch-based testing benchmark is introduced to evaluate the performance of models in real-world circumstances. This benchmark focuses on both human face manipulation and scene-level editing. The authors collect a number of face and scene-level images from the internet and request users to imagine how they would edit such images and draw corresponding sketches and masks. The collected test protocol is able to cover a series of real-world applications, such as object removal and face manipulation. Experiments are implemented on ImageNet, Celeb AHQ, and Places, with the performance of compared models evaluated using quantitative metrics, including PSNR, SSIM, and FID. The performance of compared models is also evaluated on their test protocol, using metrics such as inception score, IS. The research investigates the application of advanced machine learning techniques to improve the accuracy of predictive models in the field of climate science. Specifically, it explores the use of neural networks to forecast weather patterns and climate trends with enhanced precision. The study emphasizes the importance of incorporating large datasets and utilizing novel optimization methods to overcome the limitations of traditional models. The findings suggest that the proposed approach can significantly improve the reliability of climate predictions, particularly in regions with limited observational data. In Figures 4 and 5, we present qualitative results of face restoration in scene editing using user-drawn sketches, comparing our proposed method to existing techniques such as DeepFill v2, DeepPS, Llama, SketchEdit, and ZITS. The top two rows of Figure 4 illustrate face restoration with synthetic sketches, while the bottom two rows showcase face editing with user-drawn sketches. Similarly, Figure 5 demonstrates scene editing with user-drawn sketches. For clarity, the visualization of masked input with sketches is also included in both figures. SketchRefiner, a two-stage system, bridges the gap between sketch-like inputs and current image inpainting models, focusing on restoring complex structures in corrupted regions with potential for real-world applications. The system's effectiveness is analyzed through ablation studies on its components. The Sketch Refinement Network, SRN, Edge Map, M, and Local Coherence Constraint, LCC. Quantitative results on the Celeb AHQ dataset demonstrate that incorporating SRN, M, and LCC significantly improves performance in terms of peak signal-to-noise ratio, PSNR, Structural Similarity Index, SSIM, and Frechet Inception Distance, FID, metrics. Qualitative results support these findings, with the best visual outcomes achieved when all components are used. The importance of SRN and spatial feature alignment, SFA, block within SketchRefiner is further evaluated. Ablation studies on the ImageNet dataset show that both SRN and SFA are crucial for achieving high-quality image reconstruction, leading to substantial improvements in PSNR, SSIM, and FID metrics. However, SketchRefiner has limitations, particularly in over-refining sketches with meticulous structures. Future work aims to balance the requirements of sketch controlling ability and tolerance of sketch randomness. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. The research emphasizes the significance of nested U structure for salient object detection, leveraging conditional random fields for scale-invariant contour completion. Instance normalization is highlighted for fast stylization in image editing, while transformers are crucial for high-fidelity pluralistic image completion. The need for robust and controllable image editing is stressed, drawing examples from various papers on image inpainting and object detection. The sketch simulation algorithm, SSA, is a novel approach to simulate the misalignment, incoherence, and abstraction inherent in sketches. By projecting pixels in the convolution kernel to others fitting a Gaussian distribution, the SSA effectively captures the variability of real-world sketches. The algorithm adapts to spatial variations in the recomposed sketch by modulating the deformation magnitude psi, ensuring robust performance in diverse scenarios. The SketchRefiner employs two modules, the registration module, ERM, and the enhancement module, M. The loss functions for these modules are defined as LRM equals LL1 plus lambda 1 LCC and LEM equals LL1 plus lambda 2 LCC, respectively. These functions combine L1 loss with coherence loss, weighted by lambda 1 and lambda 2, to optimize the registration and enhancement processes. The sketch-modulated inpainting network, SIN, is trained using a multi-term loss function, LSIN equals lambda L1 LL1 plus lambda advaladiv plus lambda FM LFM plus lambda HRF LHRF. This loss function balances L1 loss, adversarial loss, feature matching loss, and high-resolution feature loss to generate high-quality inpainted images. The training strategies for the SketchRefiner and compared methods involve the use of the Atom optimizer with learning rates and batch sizes tailored to each approach. The test protocol evaluates models in a self-supervised manner using synthetic masks, allowing for a comprehensive assessment of their performance. SketchRefiner, a cutting-edge tool for refining and enhancing facial sketches, encounters challenges in specific scenarios. For instance, it struggles with misaligned sketches and can over-refine details, leading to suboptimal results. However, a user study comparing SketchRefiner with other methods reveals a significant preference for its outcomes, particularly in terms of user-perceived visual plausibility. The model's scalability is also an important aspect, as demonstrated by quantitative results on the Celeb AHQ dataset. These results showcase the competitiveness of SketchRefiner in handling large datasets efficiently. The network architecture section provides a detailed overview of the components that make up SketchRefiner, including the registration module, enhancement module, partial sketch encoder, and texture restoration module. This comprehensive breakdown highlights the technical capabilities and limitations of SketchRefiner, emphasizing its strengths in user-perceived visual plausibility and scalability. In conclusion, while SketchRefiner faces challenges in certain situations, its overall performance and user preference make it a valuable tool for facial sketch refinement. Its ability to handle large datasets efficiently further solidifies its position as a competitive solution in the field. The Progressive Sketch-to-Image Network, PSIN, and its Scene Parsing Network, SPN, are subjected to an ablation study to elucidate the coarse-to-fine guiding effect of each component on the model's overall performance. The study begins by investigating the impact of utilizing features from different layers of the SPN in the PSIN. A comparison of the results reveals that incorporating features from all layers of the SPN significantly enhances the quality of the generated images, with the best result achieved when using all extracted features in the PSIN. In contrast, previous edge-based methods, which concatenate the sketch as an additional channel of the inpainting network, fail to introduce the sketch condition and produce unguided results with artifacts due to the feature diminishing problem. The proposed method outperforms these approaches, demonstrating the effectiveness of the PSIN in generating high-quality images. The scalability of the proposed spatial refinement network, SRN, is further explored by integrating it with other state-of-the-art methods, including DeepFill v2, ZITS, and SketchEdit. The results show that the SRN significantly contributes to the performance of these methods, eliminating the free-form randomness of sketches and suggesting its potential as a plug-and-play tool for other sketch-based image inpainting methods. An ablation study is also conducted on the architectural design of the spatial feature aggregation, SFA, blocks, comparing the results when not using any design for aggregation, using SPADE, and using the SFA. The results demonstrate that the SFA significantly outperforms the other methods, highlighting the importance of the SFA blocks in the proposed model. The architectural design of the proposed SketchRefiner, SR, and its effectiveness in refining sketches for image manipulation tasks are the primary focus of this section. It begins by examining the impact of increasing the number of features injected into the inpainting network, which demonstrates improved performance and more explicit edges and textures in generated content. This suggests that the coarse-to-fine guiding features in different layers of the proposed progressive sketch enhancement, PSE, provide multidimensional information in different granularity, highlighting the efficacy of PSE in handling sketches in the latent space. An ablation study on the architectural design of the proposed spatial feature alignment, SFA, is then conducted, comparing it with the SPADE block 30. The results, presented in Table 8 and Figure 10, show that not using any specific design in the inpainting network to fuse extracted features leads to apparent color discrepancy and blur, proving the necessity of the proposed SFA. Using SPADE 30 in SketchRefiner results in artifacts due to the gap between different latent spaces, further emphasizing the importance of the proposed SFA for optimal results. Additional results, including the visualization of refined sketches and corresponding inpainting results in Figure 14, and more results of face manipulation and scene editing on the testing benchmark in Figure 15, are also provided. Furthermore, an interactive demo is designed for end users to experience the process of sketch refinement and interactive image inpainting based on Gradio 1. The user interface of the interactive demo is shown in Figure 13, where users can upload an image for manipulation, customize their own mask and sketch interactively, and view the inpainted results with sketch refinement. A demo video of the interactive demo is provided in the supplementary materials, and the interactive demo will be released upon acceptance of the paper. In summary, this section reinforces the importance of the proposed PSE and SFA components in enhancing the quality of sketch refinement and image manipulation tasks. It demonstrates the effectiveness of the proposed approach through ablation studies and additional results, while also introducing an interactive demo for end users to experience the process firsthand. The paper introduces a novel approach to image-to-image translation, focusing on the challenging problem of sketch-to-image synthesis. It proposes a multimodal dataset comprising images, masks, and sketches, enabling the exploration of various translation tasks. The test protocol showcases the diversity of the collected dataset, including images, their corresponding masks, and sketches. The authors employ a two-stage approach, first translating sketches to masks using a generative adversarial network, GAN, architecture, and then translating masks to images. The network is trained using a combination of reconstruction loss, adversarial loss, and perceptual loss. This decoupling of the translation task allows for more effective and flexible image synthesis, enabling the incorporation of additional modalities like text or audio. The interactive demo's user interface is depicted in Figure 13, starting with an image upload requirement for manipulation. It features sketching areas on the left side where users can customize their desired mask and sketch interactively. Users can turn on sketch refinement by clicking a checkbox. Simultaneously, the corresponding inpainted results are displayed on the right side. The clear button allows users to erase all their samples, and the flag button enables saving the uploaded image, customized mask and sketch, and corresponding result locally. The registration module, in the proposed architecture, SRN, consists of an encoder-decoder structure with skip connections. The encoder comprises 7 gated convolutional layers with leaky ReLU activation and instance normalization, followed by 2 nearest upsampling layers. The decoder mirrors the encoder's architecture. The enhancement module, in SRN also employs an encoder-decoder structure with skip connections. The encoder consists of convolutional layers with ReLU activation and no normalization, while the decoder uses residual convolution blocks with ReLU activation and no normalization. Nearest upsampling layers are used for upsampling. The partial sketch encoder, PSE, consists of gated convolutional layers with ReLU activation and batch normalization, followed by residual convolution blocks with ReLU activation and spectral normalization. The network architecture is designed to process partial sketches. The texture restoration module, TRM, in SRN employs a combination of vanilla convolutional layers, transpose convolutional layers, and fast Fourier convolutional layers with ReLU activation and batch normalization. Spatially adaptive normalization is used in some layers. The output of TRM is processed through a final vanilla convolutional layer with tanh activation. These modules are essential components of the proposed SRN architecture, which aims to perform image-to-image translation tasks. The specific architecture designs and normalization techniques employed in each module are critical to the overall performance of SRN. Figure 14 provides a visual representation of the refined sketches and corresponding inpainting results, demonstrating the efficacy of the proposed method. The figure consists of 5 columns, each representing a different stage of the process. Column A displays the original image, while column B illustrates the input with the sketch, where the masked regions are visualized. Column C shows the final inpainting result, demonstrating the successful completion of the missing regions. The sketch refinement process is depicted in columns D and E. In these columns, the gray strokes represent the sketch strokes in the mask regions. The refined sketch in column E exhibits a more accurate and detailed representation of the original image, highlighting the importance of the refinement step. The visualization underscores the importance of the sketch refinement process in generating high-quality inpainting results. The figure provides a clear illustration of the proposed method's ability to handle complex image structures and accurately complete missing regions. The refined sketches, in particular, demonstrate a high degree of accuracy and detail, enabling the generation of realistic and coherent inpainting results. This visualization supports the quantitative results presented earlier, further validating the effectiveness of the proposed approach. The figure presents qualitative results of face manipulation in scene editing using the proposed test protocol, showcasing the efficacy of the approach. The top row depicts face manipulation, while the bottom row illustrates scene editing. Each set consists of the original image, input, and result. Notably, the input images display visualizations of masked inputs with sketches, facilitating the manipulation process. These visualizations enable the model to focus on the desired regions for editing. The results demonstrate the model's ability to accurately alter facial features while preserving the overall identity and realism of the face. The scene editing results exhibit the model's capacity to effectively modify objects within the scene, such as changing the color or removing objects. These qualitative results corroborate the quantitative findings, further solidifying the effectiveness of the proposed approach in image manipulation tasks. The use of masked inputs with sketches allows for more precise control over the editing process, enabling the model to produce high-quality results.